Hello. For this video, we will be talking about the last topic under PERT-CPM, which is crashing activities. To start off, let me first define what crashing means. To crash an activity is to speed up an activity duration. This is usually done by spending an amount to either speed up the duration per some unit of time. So, for example, you may spend 300 pesos to reduce the activity duration per day, or you can also reduce the activity duration by a fixed amount of time. For example, you can spend 1,000 pesos to reduce the duration by 5 days. So in this case, in the second example, it's usually a package deal where you will have to spend 1,000 pesos and the effective reduction in the activity duration is 5 days. In the first example, you have the liberty of deciding how many days you'd like to crash a certain activity. It is important to note that in both cases, what we are actually doing is we are reducing the activity duration, how long it will take you to do a particular activity. This topic is very much important because there are a lot of projects where their activities can be crashed. Let me give you a quick example. Let's say you're the editor of your yearbook, and according to your printer, your supplier for your yearbook, they are able to print your yearbook, let's say for 100,000 pesos, but it will take them 3 weeks. On the other hand, uh, it is very possible that they will offer you some deal wherein you bump up the cost to 150,000 pesos, and you will be able to get your yearbook in just 2 weeks. So there was a reduction of 1 week at the expense of an additional 50,000 pesos cost. Okay, you will see this in a lot of activities. Um, Another example may be getting your driver's license. If you don't pay grease money, you'll be able to get it, let's say, 3 days. But if you pay grease money, then you don't even have to go to the LTO office to be able to get your license right away. What I have here is a very simple problem with certain information. So we have a project with 10 activities, activity A to J, and of course their predecessors. Instead of having just a single duration for each of the activity, what I have here, what I have here are two values, the normal duration and the crashed duration. Okay? Let me explain what normal duration and crashed duration are. Normal duration is usually seen as the duration of the activity on a regular day or normally. Okay, so without spending additional money, normal duration is how long your activity will last. However, each activity will have a crashed duration. And what is this crashed duration? Crashed duration is the number of time that you can reduce your activity duration. So for example, for activity A, normally it will last 5 days. However, if you spend some money, you can bring down the activity duration down to 3 days. Okay. The next two column are costs associated to the different activities. The normal cost is the cost of doing particular activity at its normal duration. The crashed cost, is the cost of doing a certain activity at the crashed duration. So again, using activity A as an example, if you do activity A for 5 days, then it will cost you $2,000. However, if you bring down activity A's duration down to 3 days, then it will cost you 3,000 pesos, $3,000. Okay. Now, what I have here are the four parameters that are seen in the table. So I have norm I. Norm I is the normal duration of activity I. So that is this column, normal duration. Next is N cost or normal cost sub I, which is the cost of activity I at normal duration. And that is this column, normal cost. Next is crashed I, which is the crashed or reduced duration of activity I, and that is this column. And finally, we have crash cost or C cost sub I, and that is the cost of activity I at the crashed duration, and that is this last column. Okay? Now, given these four parameters or these four constants, we will be able to get a certain S sub I. S sub I in this case is the difference between the crash cost and the normal cost all over the duration of your normal minus the duration of your crashed. If you are able to quickly understand this, S essentially is in a way the slope. It is the cost of crashing a certain activity per unit of time. Okay? So, for example, if we take activity A, its normal duration of 5 and crash duration of 3, this means that you can actually crash activity A for 2 days. And if you look at the difference in their costs, the difference is $1,000. So what does that mean? That means if we divide 1,000 with 2 days, we get a slope or an S sub A to be equal to 500. And what is that 500? 500 is the cost of crashing activity A per day. Okay? So we will be able to compute for all of the S sub i's for all activities. And this table actually computes it for us already. Do take note that for activity D, the denominator is 0. No? Because your normal duration and crash duration are both 5. What does that mean? That essentially means you cannot crash activity D anymore. It is at its shortest duration already. Okay? However, for all the other activities, you do get some form of slope in this case or crashing cost, S sub I. So now what we have is a problem where you do have your activities and its duration and cost. However, there is a possibility of you reducing the duration of certain activities so that effectively you would like to reduce the project duration. Okay? Now, why is it important that to know that you can actually reduce your project duration? It is important because of two general questions or problems. What are the two problems? First, it is possible that you have a deadline for your project, and this parameter deadline is the parameter D. And what you would like to do is you'd like to minimize the total cost of meeting the deadline. So for example, let's say currently without crashing, your project will last for 15 days. However, your boss, let's say, tells you you need to finish your project in 10 days. And in this case, what you'd like to do is you'd like to know which activities will be crashed so that you will meet the deadline of 10 days, but you'd like to do it um, such that you will minimize the cost. Okay? And that is the first problem. On the other hand, the second problem talks about a budget given to you. Okay? In this case, the notation for the maximum budget is B. And given this budget, what you'd like to do is you'd like to minimize the project duration. Or, to explain it in an easier manner, What you are actually looking for is uh, to look for the fastest time that you can finish a certain project, given that you are willing to spend an amount B. What we have here is the graph for the base problem. So I've graphed the problem, and we have this network graph. So given these two problems, what is the best way to deal with these two uh, questions? The best way to deal with these two questions is via linear programming, which means we need to define some variables and come up with a linear program uh, so as so that we can achieve these two requirements. So what are the decision variables for this particular linear programming model? We have two. Let x sub I be the duration of activity I. X sub I is the duration of activity I means that, for example, in activity A, we are deciding how long we will have to do activity A. Okay? Eventually, we will have a constraint that says x sub A is between 3 and 5 because 3 and 5 are the possible durations of activity A. At its slowest, it is 5. At its fastest, it is 3. But it should be clear that x sub A, which is the decision, is a decision where we are deciding how long activity A will be done. Okay? So that is your x sub I. The next variable is y sub I. Y sub I is the duration of the longest path from the start to activity I. And we will need this because there will be some requirements for the project duration. What I'd like to do now is to show you the linear programming model for the two problems we talked about. Before I show you the linear programming model, let us review again the two problems we were talking about. Okay, so the first problem talks about a certain deadline D, and you'd like to minimize the total cost of meeting the deadline. The second problem, we will just interchange. You are now given a certain budget, but and would like to minimize the project duration. So for my linear programming model, we will first address this first problem. So what I have here are the network graph and the parameters of the problem. Okay. I also have our decision variables. Because our first problem talks about minimizing the total cost of meeting the deadline, then your objective function should be your total cost. And what is the total cost of meeting your deadline? The total cost of meeting your deadline is essentially the sum of the individual costs of each activity. Okay? Now, what is the cost of each activity? The cost of each activity is essentially the S sub I, its corresponding S sub I, which is the cost per unit of time that you'd like to crash activity I, multiplied by how much you are crashing activity I. And in this case, the amount of days, for example, that you would like to crash activity I is its normal time minus your decided activity duration. So if normally activity A is 5 days, and you decide activity A's duration to be, let's say, 3.5 days, then you are effectively crashing activity A by 1.5. And this 1.5 days, you are multiplying by its corresponding rate. Okay? And all you have to do is just get the sum of all those individual costs per activity to get your total cost. Now, on to our constraints. Because x sub I is the duration of your activity I, it has to be between the two given values. It has to be greater than the lowest possible value, which is your crashed sub I, But it also has to be less than or equal to its highest value, which is the norm sub I. Okay, so you have this constraint. Secondly, because we were given a deadline, then y sub finish has to be less than or equal to the deadline. Why is y sub finish in this case the left hand side? Because remember, what is our definition of y sub I? Y sub I is the duration of the longest path from start to activity I. And if you want to determine the project duration, what you'd like to do is you'd like to get the duration of the longest path from start to activity finish, which in this case is the variable y sub finish. Okay? And because of the deadline, we'd like y sub finish to be less than or equal to the deadline. Now, we do not end here. We do have other other constraints that we have to take into consideration. What are the other constraints that we have to take into consideration? We have to remember that we need to model our longest path model. We have to look at y sub I and say that y sub I actually is a dependent variable. It depends on the prerequisites and your x sub I. It depends on how long you are deciding to do activity I. And therefore, the next, so let me box out these constraints. The next set of constraints will actually make sure that you will correctly get or compute for y sub I. Or in this case, y sub I will accurately tell you the duration of the longest path from start to activity I. Let's start. So looking at your network graph, we shall start with the start node. And in this case, we can easily say that y sub start, or the duration of the longest path from start to start, is equal to 0. I think that's obvious. Next, if you look at y sub a, the duration of the longest path from start to activity A is actually the duration of the longest path from start to start plus the duration of activity start. And that is this. No? That is why y sub a is equal to y sub start plus 0, because 0 is the duration of the starting node. In the same manner, look at y sub b. If you look at node b, it only has one incoming arc, no, or inbound arc to getting into activity B, and that incoming arc comes from activity A. Therefore, the duration of the longest path from start to B is equal to the duration of the longest path from start to A plus the duration of x sub A. And that is why you have this. You do the same thing for y sub c and y sub d. Why? Because there is only a single inbound arc for each. No, looking at node C, there is only one inbound arc coming from A, and that is why your y sub c is equal to y sub a plus x sub a. The same goes with y sub d. Your incoming arc comes from A. That's why y sub d is equal to y sub a plus x sub a. A good example for a different way of modeling this is uh, node E. If you look at node E, there are two inbound arcs. One arc coming from B and the other arc coming from C. So technically, y sub E, which is the duration of the longest path from start to activity E, is equal to the biggest. That's why we have the maximum function. It is equal to the biggest between the one coming from B. That's why you have your y sub B plus x sub B, and the one coming from C. That's why you have your y sub c plus x sub c. Okay? We will leave this as it is right now, for now. Okay? And we will deal with this later. Node F, G, and H will also have equality constraints here because if you look at node F, G, and H, they all have a single inbound arc coming from B, C, and D. That is why you have these constraints. In the same way we did Y sub E, if you look at node I has two inbound arcs, one coming from F, the other one coming from G. And therefore, Y sub I is the biggest, okay? The biggest between the one coming from F and the one coming from G. Y sub J, or node J, has a single inbound arc, so Y sub J is just this. And finally, Y sub finish has two inbound arcs. So Y sub finish is equal to the maximum between the one coming from I and the one coming from J. And of course, we have our non-negativity constraints. Now, how do we deal with the maximum functions in our model? If your y sub j is equal to the maximum of y sub I plus x sub I for all I such that I comma j exists. So in this case, no, our j here is node E. Our node i's are node B and node C because BE exists and CE exists. If you look at the graph, we have our BE exists and CE exists. Okay? So if you have this constraint in your model, we can easily convert this to a linear programming model by adding several constraints, one constraint per node I. Okay? And what is a constraint? What you need to do is you need to say y sub j is greater than or equal to y sub I plus x sub I for every I. For example, given that y sub e is equal to the maximum between y sub b plus x sub b and y sub c plus x sub c, then we can convert this maximum function into two constraints. What are the two constraints? First, y sub e is greater than or equal to y sub b plus x sub b, and no and y sub c is sorry y sub e is greater than or equal to y sub c plus x sub c. In the same manner, if y sub I is equal to this, the maximum between y sub f plus x sub f, comma y sub g plus x sub g, then we have these two constraints. And we also do that for the finish node. So all you have to do is replace your maximum function with these constraints. And what you will have is a linear programming model. Okay? So these three boxes will replace these three constraints. This one, and this one. Okay? This is our linear programming model for the first problem, which talks about the deadline D. In this case, your deadline is here. Okay? And you'd like to minimize the cost of meeting the deadline. And that's why your objective is this. Now, how do we deal with the second problem? Where the second problem looks for the, or you'd like to minimize your project duration, but you are given a certain maximum budget. What happens here is exactly the same, except these two will be switched. What do I mean? What do I mean? In this case, your objective function now becomes minimize z equals y sub finish. Okay? Why? Because if you look at the objective here, you'd like to minimize project duration, and project duration is modeled as y sub finish. Okay? And then, oh, of course, you still have this constraint, but your budget model will now become a constraint. So in this case, the sum of your S sub I norm of I minus X sub I for all I has to be at most your budget. And everything else will be the same.